Hello. Last time we derived the Friedmann and Raychaudhuri equations of cosmology. Let's apply what we have learnt to determine a rough estimate for the diameter of the observable universe. We will model the universe as consisting of two types of matter: pressure-free dust, that is ordinary matter, and a cosmological constant, which is also known as dark energy. We will neglect the presence of radiation in this computation, as this is only dominant for a small fraction of the age of the universe. The matter and dark energy obey the equations of state P equals 0 for dust and P equals minus rho c squared. So P is the pressure, rho is the mass density, c of course is the speed of light. Since matter and dark energy do not interact with each other, they obey the fluid conservation equation independently of each other, which is that thing which we learned from last time. So P equals 0, we just get rho dot over rho is equal to minus 3a dot over a. So therefore rho is proportional to a to the minus 3. That's dark energy. So for dark energy, then of course we get 0 here, so we just get rho equals constant. So let's write rho for the matter equals rho m times a to the minus 3 for some constant rho m, and rho dark energy, I just write it as rho lambda. Dark energy corresponds to the same thing as a cosmological constant. Now the K equals 0 Friedmann equation is a dot squared is 8 pi g over 3 times the total mass density times a squared. So that will give me rho m over a plus rho lambda times a squared. What we'll be doing is setting t0 to be the current time and a of t0 is 1, so then rho equals rho m and rho equals rho lambda are the values observed today. To solve this equation, we're going to write a as b to the alpha. So you get alpha squared b to the 2 alpha minus 2 b dot squared, 8 pi g over 3. Let's take rho m out as a factor. We'll have a b to the minus alpha plus rho lambda over rho m, b to the 2 alpha. Or if we rearrange that, b dot squared is 8 pi g over 3 alpha squared, b to the 2 minus 3 alpha plus rho m over rho lambda times b squared. Just check that I've got that around the right way. That should have a rho m there, and that should go the other way. Okay. If we take alpha to be equal to 2/3, then of course this thing becomes 1, and so we get b dot squared is 6 pi g rho m 1 plus rho lambda over rho mb squared. Or integrating this, the integral 0 to top value for b at x. B is a to the 3 over 2 db over root 1 plus rho lambda over rho m b squared, and that's equal to the integral of that dt, which is just going to be t. We always measure time from 0 when there's a big bang. Okay. Let's now form this integral. So if I multiply by root rho lambda over root m and cancel it off there, then that term just gives me the inverse sinh square root of rho lambda over root m a to the 3 over 2 6 pi g rho m t. Obviously gives me that. Rearranging this, I'll get a at t is rho m over rho lambda, and because of that power there, that'll make that a third. Sinh to the 2/3 root 6 pi g rho lambda t. So that's my expression for the scale factor of the universe in this case. Now, if we were to set rho lambda to be 0, where you take the limit as rho lambda goes to 0 in here, that gets rid of the cosmological constant term, the dark energy. All you're left with matter, and you'll end up with a of t proportional to t to the 2/3. You can see that this thing gives you the limit. This goes to 0, gives you a t to the 2/3 power. We're only interested in the time dependent, not the particular scaling. That's known as the Einstein-de universe. And that's also what we get at small times, something resembling the Einstein-de universe. If we take rho m goes to 0, we're not interested in the overall scale here, so we can get rid of that factor, and we'll just get something which is going to be proportional to an exponential of e to the lambda t at late times for some lambda. And of course that's going to be 2 over 3 root 6 pi g rho lambda. And that's the de Sitter universe. The de Sitter universe has the property that h, which is a dot over a, that's the Hubble parameter, put into there, that's lambda, that's constant. And this is the space-time which corresponds to the steady-state universe. Find the density parameter. Omega lambda is 8 pi g rho lambda over 3 h naught squared. So this actually is the density parameter at the time t naught when h equals h naught. Then 6 pi g rho lambda, put in here, that's 9 over 4 omega lambda h naught squared. That'll be useful to us. Our objective is to work out the distance to the cosmological horizon. So for a light ray you have ds squared equal to 0, and that's equal to minus c squared dt squared plus a of t squared times dx squared. So x is going to be the integral from x to 0 dx, which from this thing to 0 will give me c the integral 0 to t prime over a of t prime. The idea is that, supposing we have 2 points in the universe, this point x, this is us at the origin. We're interested in light coming from x to us in a time t. Now, the lower limit is 0 because that's the earliest time a light ray could have set off from x. So in order to reach us we need this equation to hold. the distance is then r is ax, is c a the integral dt for a of t naught t. So that's my distance to the cosmological horizon. If the universe did not have a Big Bang, then of course we would have the zero replaced by minus infinity. One thing we can notice immediately from this equation is that r dot is c a dot the integral naught to t dt over a of t, right on there, plus differentiating that just gives me c. That's strictly greater than c if we're in an expanding universe. So the rate of recession of the cosmological horizon is always superluminal. Okay, I have an expression for a here, and this is the distance to the cosmological horizon. So let's work out r over c. That's twice sine 2/3 3 over 2 root omega lambda h naught t So what I've done is substituted this thing into this equation. I've made a change of variables just to make this thing slightly nicer, and that brings out this factor out here. Okay, we're going to take t equal to t naught, the current time. Let's just work out what h naught is. It's a dot over a at t0. So that's log a dot at t equals t0. So since we're taking the logs and then differentiating, this constant doesn't make any difference. We're going to get 2/3. We're going to get root 6 pi g rho lambda. We're going to get a cosh over a sine, which is a coth. Lambda t. Okay. That was the same thing as 2/3. That quantity was just that quantity there, so it's 3 over 2 lambda h naught coth 3 over 2 root omega lambda h naught t naught, and that's equal to h naught. Those cancel. That's 1. So we get tanh of 3 over 2 root h naught t naught is equal to root omega lambda, which actually gives us a formula for the current time. Where's tanh? That thing divided by 3, that thing times h naught. We'll put some numbers into that later on. Now, sinh occurs here. We know what the tanh is. Well, we know that cosec squared of a number beta, let's call 3 over 2 root omega lambda h naught t beta. That thing is coth squared minus 1, so sinh beta is 1 over root coth squared beta minus 1, which is tanh beta over root 1 minus tanh squared beta, which is the square root of omega lambda over 1 minus omega lambda. So this thing gives me R over C is 2 over 3 H naught. We'll get, we want this to the power 2/3, so we'll end up with a 1 minus omega lambda is the 1/3. We get this thing to the 1/3, but we also had it in the denominator here, so that gives me 1/6 integral 0. This limit here is going to give me an inverse tanh root omega lambda d theta over sine to the 2/3 theta. Okay, so now we just need to plug in some numbers. Observationally, we find that omega lambda is about 0.73 and 1 over h naught is about 14.3 gigayears. This will give me a value of R as 49.3 gigayears, or over C, I should say. So that's 49.3 billion light years, and therefore a diameter of 98.6 billion light years, and T naught for the age of the universe will be 14.2 billion years. If we take omega lambda is 0.7, 1 over h naught is about 14 gigayears, you will end up with R over C as 46 gigayears. In fact, the diameter will be 93 billion light years, and the age of the universe will be 13.5 billion years. So what we have done is work out the radius or diameter of the observable universe and its age from the observations, and by integrating up the Friedmann equation which we derived in the previous video.